Thank you, everyone. I'm Anima Anandkumar, and today I'm excited to talk to you about the developments at the intersection of AI and science. So previously, AI was great at being able to predict properties given an input text or an input image. But now we are in the realm of generative AI, where we've inverted the process and able to generate complex text, image, and even other aspects such as molecules and proteins. And that's where, for the scientific realm, this can be really exciting. So for instance, one of the projects we pursued last year was to use the same framework in text modeling, where we learn to predict the next word, to do that in the language of genomes, where we learn to predict the next set of nucleotides. And we train this on all the known virus and bacterial genomes. So we took about 110 million genomes, and then we wanted to ask, what are the new genomes that would be generated based on the model that's learned? So can we predict new variants of concern before they emerge? And that's what we explored in the realm of coronavirus, where during training, we only showed the variants that appeared in the first year, namely the alpha and beta variants. And this is a visualization of the latent space of the model, where you see that the similar variants are clustered together. And then we asked it to generate new variants, and it successfully generated variants that emerged later, such as Delta and Omicron. And not only that, it also generated variants that haven't yet emerged. So this is how we can be better prepared, creating better vaccines, drugs on genomes before they emerge. In order to predict how well do the variants that haven't yet emerged, what kind of an impact they have on the human body, we need to understand the molecular dynamic binding process. How do these viruses bind with molecules in the human body? And those kind of simulations today are done through numerical methods. We know equations in terms of what are these binding forces. You can go down to the quantum level, think about Newtonian forces. We have equations based on partial differential equations that can predict such motions. But in order to simulate this with numerical methods, it can be extremely slow. And we see such equations appear in a range of natural phenomena, whether it has to do with molecules binding with each other or the weather and climate of this planet. And this is where our current, even bigger supercomputers aren't enough to get down to the level of fidelity needed to capture such complex phenomena. For instance, in climate models, the biggest source of uncertainty is the turbulence in clouds that cannot be captured even with the world's most powerful supercomputers. This is where AI has a big impact in our ability to learn better features, accelerate such simulations, and sit on top of all the hardware accelerations. And we created a framework called neural operators that can learn across multiple resolutions. So unlike text models that are trained on discrete tokens, ours can capture continuous phenomenon, such as fluid dynamics, where you train at one resolution and still you can predict at a higher resolution, even if you didn't see such training data. We use that to create weather models based on all the historical weather data, and it can forecast weather really accurately and at the same time be about 45,000 times faster. And with that speed up, we can create a much larger set of ensembles to create better probabilistic assessment of tail events such as hurricanes with direct impact on human lives and economic costs. Across a range of different domains, we have managed to accelerate simulations, capture the complexity of many domains, such as predicting disruptions in nuclear fusion. Thinking about material properties, how does the material deform? What about ultrasound imaging and being able to do medical imaging through that? We are able to get speed ups of as much as hundreds of thousands of times in many of these settings, replacing traditional simulation methods with AI, creating surrogate models for capturing the complexity of many of these domains. And with that, we can also do inverse problems. So think about, once I have an ability to understand fluid dynamics, I can solve problems which require that. For instance, we recently created a better medical catheter that prevents bacterial contamination and reduces it by about 2 orders of magnitude from the previous ones. And we were able to do that by understanding fluid dynamics through AI and directly optimizing in the design shapes these triangular shapes that you see that can trap and prevent bacteria from coming into the human body. And so this understanding helps us directly capture the complexity of the design process and really reduce the time from conception to experimentation to creation. And we see that also in other frameworks such as mask design and lithography in the chip manufacturing process. And so to me, the present is foundation models of text where we can do a multitude of tasks. The future is foundation models for science where we understand all kinds of different phenomena and really capture that well. Thank you.